Now, another area that you have touched on slightly is the concept of error in measurement. And in this chapter, we're going to develop that further as well. So in 301, just a bit of revision about error. You know that we would say that no measurement is absolutely exact because there's always a degree of error, whether it's due to human error, the way we've observed the measurement, the device we've used may have some error contained in it. And the other reason that we say that no measurement is exact is because we could always attempt to make our measurement correct to more decimal places. For example, if you were measuring a millimetre to the nearest millimetre, then if you had the device and the facilities, you could measure possibly to the nearest 0.1 of a millimetre, and it doesn't stop there. Why couldn't you measure if you had, enough enlargement and a device appropriate to measure to 2 decimal places? And so on and so on. So we always say that no measurement we take is exact. Which then means if we're using these measurements in other calculations like area, then our area is also not exact. Now, in the past, we've never considered this aspect of area, and you will only consider the aspect of area when the question refers to it. So you're doing a standard area and volume style question, there seems to be no reference to error, then you will answer as directed by the question to the nearest millimetre, to the nearest square centimetre, whatever, and you don't need to worry about it. The questions that will require you to make an adjustment should be obvious, but I'll talk about that when I talk about 310. So the error is determined, like I've just said, by the device, and in particular the smallest marking on your device, which is referred to as the precision of how precise your device is. And then, of course, the absolute error is half the precision. So we know from previous work that the absolute error is half the smallest unit of measure, and if you've forgotten, the smallest unit of measure is called the precision, and it probably makes sense because it's how precise the device is, and it's indicating that you should complete this by calculating the absolute error for each device. So this first ruler here, it's being measured in its smallest unit of measure is a millimetre. Each little increment marks off 1 more millimetre. So the smallest units are 1 millimetre, giving us then the absolute error, which is half the smallest unit. Half of that is 0.5 of a millimetre. This second ruler, now this is not a common unit for us in Australia. We don't use feet and inches anymore. But this device is measuring not to the nearest inch, because from here to here is 1 inch. If we look at how it's broken up, then there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 little increments, and we would say that the smallest unit is 1/16 of an inch. 1/16. Each little line is marked off, or 1 inch is broken up into 16 equal parts, which gives us each line at 1/16 of an inch. So that is the precision, or the smallest unit. And then if I multiply that by a half, or take a half of 1 in 16, then 1 times 1 is 1, 2 times 16 is 32. So we would say the absolute error is 1/32 of an inch. I haven't done all of the devices over here. I've just done this first one. And as you can see, there is only one unit of measure, and it's 50 mil. So the smallest unit is 50 mil, and we'd say the absolute error is 25 mils, just half of that. Sometimes we're just given a straight out measurement, and we have to be able to work out what the absolute error of that measurement would be without knowing or being able to see the device that was used to measure and give us that measurement. So when we do that, then we look in particular at the measurement, because that's all we will have. For example, a measurement of 37 millimeters. Now, the fact that it could go to 7 millimeters is probably suggesting that the device has as its smallest unit of measure 1 millimeter. We know that it's not we know it's not 2 millimeters, or our number here would have to be an even number, 36 or 38. The fact that it can be given to 37 and it wasn't given to any decimal places indicates that it's probably just going up by 1 millimeter. And like we said before, that would give us an absolute error of 0.5 millimeters. Now, this absolute error will become important when we're calculating percentage error. If you've got a measurement of 135 and you're told it's to the nearest 5 centimeters, then this is telling you what the precision is, or what the smallest unit of measure is, and it's 5, and half of that is 2.5. So the absolute error of that measurement, given this detail, would be 2.5. If we weren't given that detail, we'd probably assume, as we did above there, that maybe the measurements were going up by 1 centimetre. Then a measurement of 3.7 minutes. So now we've got 0.7 of a minute. We would say that we can measure to the nearest 0.1 of a minute. Otherwise, the measurement shouldn't be given with a decimal place. And so the absolute error, half of that, now be careful, take your calculators if you need, and do a half times 0.1, and you'll get 0.05 minutes. There are 2 reasons for calculating the absolute error, and one, which I've already said, is when we're calculating percentage error, and we are using this formula. Percentage error is absolute error over the measurement times 100. The second place that you will use absolute error is if the question asks for the limits of the measurement, So a measurement is always considered to be the recorded measurement plus or minus the absolute error. Okay, let's have a think about it. We just established before that for 37, the absolute error would be 0.5. We've said it's going up by 1 millimetre, and half of 1 is 0.5. The limit of this measurement, it could be as big as 37.5, or it could be down as low as 36.5. It's somewhere between those two. And in fact, we say it is less than 37.5 because if it was exactly on the 0.5, we would round the measurement up. 135 has limits of 135 minus the 2.5, which takes you down to 132.5. Please take your calculator and check these. Pause the video if you need to, just so that you know where these numbers have come from. And 135 plus your 2.5 to give you 137.5. The range of all possible values for 3.7 minutes would be, now we want 3.7 is in between 3.7 minus 0.05 and 3.7 plus 0.05. We'd say that the measurement 3.7 minutes is somewhere between the minimum of 3.65 minutes and a very maximum of 3.75. And again, like I said, pause the video, take your calculator, check you know where these numbers are coming from, because you could get a question requiring you to actually come up with these numbers. Percentage error is, well, you know, before you can get a percentage, you must have a fraction. Before you can get a percentage, you must have a fraction. Here you can see your fraction. Your fraction's made up of the absolute error. And that's just what we've been talking about. But in this case, you put it over the measurement, you make your fraction, you multiply that by 100 to turn it into a percentage.